Hi, Sam Roberts here for ProRaster Scientific. Let's take a look at the Classify Polygons operation. So on the processing menu, you'll see that there's a Classify Raster and Classify Polygons operation. And here's the dialog box. So this is going to take a collection of polygons and convert them into a raster. So another term for this is vector to grid or rasterize, but I call it a classification operation because what we do is we produce a classified raster. And in fact, this operation is more like a convert operation because otherwise, unlike other classification or rasterization procedures, this takes all of the information that's in your original GIS table and brings it all across into the output raster. So how does it do that? Well, it creates a classified raster. So in your table, and I should point out at this stage that that the table has to be in MapInfo professional format. So if you have a table in some other format, like for like shapefile or something like that, you need to convert it into a MapInfo table format. So what that looks like is essentially a matrix. So you have a table with a bunch of columns and a bunch of rows. Each row has a geometric object associated with it, and that can contain one or potentially many polygons. It can contain other things too, like lines and points and so forth, but if they're found, they're ignored. We're only looking for polygons in this case. So you've got your geometric information. You also have some style information associated with each row, and that tells the system how to render those polygons. So it's going to have a color in it, and we're going to usually go and grab that color in order to colorize the polygons in our own, or colorize the pixels in our raster. And then there'll be a number of columns in that table. Might be many columns in that table, and they'll contain all sorts of data. So it might be might be text data, might be some kind of numeric data, it might be dates and times and so forth. All of that information is able to be brought across into a classified raster. So what's a classified raster? Well, a classified raster is a raster that has one concrete band, and that's an index. So it's an unsigned integer of some size. It's zero based, and it simply points into the row number in your classification table. And you can think of that as being the table that's in your GIS table. So it just stores a row index. And when you the first band for a classified raster will be that row index. The second band will be the first column of the classification table. Third band will be the second column of the table. So all of those columns in the classification table are exposed as band data through the raster interface. And so you can treat a classified raster just like any other raster. So the data that's in those columns, you can access that data via the mechanism where if you look for a cell value, firstly it gets that index, and then it goes and looks up in the table, and then it grabs the value from that table, from the appropriate column for the band that you're asking for. So that's a classified raster. So the Classify Polygons operation firstly requires you to specify your vector file. So that's going to be a tab file. So let's go to the DC land use. So this is an example file that ships with MapInfo, for example. And I have MapInfo running here, and this is the file that we're looking at. So you can see it's a bunch of polygons, got different coloration, and and when we load that table into Classified Polygons, the first thing we do is we get a list of all of the columns in the table. And so you can see them all here, and they have some information after them. So some of them say text. in brackets. That just indicates to you that that column contains text data. And then there are some other ones, like for example this MI style, which is the rendering style object that's associated with each row in the table. That's got this brackets color after it. And we'll see how that relates to these settings over here in a minute. So that's our input data. Here we've got our output data. So we just browse to the output MRR file that we want to produce. We're only going to produce MRR files. We won't produce any other format of raster from this operation. And then I can just hit OK and it will go and do it. But you do need to look at the cell size before you do that. So we don't set a default cell size that's appropriate for the table that you've opened. You have to set the cell size yourself. And in this case, we need to set a very small cell size. These are in geographic coordinates. So I'm going to set something like really small, like really, really small. I'm going to go for about 1 meter. So that's 10800. We'll come back to this in a minute. I'm just going to assign a label, hit OK, and it'll do the processing. And here is our result. So you can see it's the same as this thing, almost the same. You'll see some spots where there'll be just a little difference. So, so here you can see there's some red in here and then red out here. You go over here, we've only got this, this red, we haven't picked up this polygon. And that's because those polygons are overlapping. So when we bring that across into the raster, anything that's overlapping is going to be resolved down to one of the polygons. One or the other, it's going to choose one. And so we'll lose that kind of information. So where you have overlapping polygons, you're going to get a result that's not quite, well, the point is you shouldn't have overlapping polygons for this kind of operation. Look up the key data value and it'll tell you what what these polygons are from that label. So let's go back and take a little bit of a closer look. So here's all my columns. How can we manipulate this? Firstly, I can delete columns if I don't want them brought across into my output raster. So I just select the column and hit the negative button and that will delete it. So I'll delete that one, I don't want that one, I don't want that one or that one. So now they won't be included in the output raster. If I've made some kind of mistake or I don't like what I've done, just hit this button to reset the list and you can start again. Now, there's a little drop list here with some values in it. So there are some special codes that tell ProRaster something important about different columns in the classification table. And the most important one from a user's point of view is the label. So if you can, it's a good idea to specify that one of the input columns from your GIS table corresponds to a label. So in this case, you know, we've got smart label here. That's actually our label. So let's select that and call it our label. And you can see that we now have label up here in brackets. Down here we have color in brackets. And that's the second important piece of information that we need. If we don't get a color out of the polygons, then they're all going to be the same color. And we'll have to use some other different mechanism in ProRaster to colorize the polygons differently. So in here, we have class, value, color, label, data, red, green, blue. So color is a red, green, blue color RGB value. And that's the primary thing that we'll be looking for. If you don't have that, you can specify red, green, and blue separately as a color. Label is our text label. That's an important one. Whenever we browse, whenever you move your cursor over the raster, the label will be shown as the cursor value. And then we have these two here, class and value. So the class is used to indicate that this was the original class index for the table. So it might have been some value like 92, for example, but once it got put into the classification table, everything was compacted and it became zero-based, and it might only be index number 17. But the original class value might have been 92, so that's what we store there, and it doesn't make any difference to anything. You can set it, or if you don't set it, it doesn't make any difference to anything. Value is the primary value in the raster, the primary data value, and you can set it to anything. Again, it doesn't make any difference to anything. And then this data setting, that's for everything else. So anything that isn't one of these other special values, it will just be labeled as a data value, and you can assign that to anything. And so all of these things will be assigned data by default, and that's what will actually be recorded in the raster. So we've got our label, we've got our color. When we do our import, that information will be recorded in the raster, and so we'll have labels displayed and we'll have colors in use. So let's skip this now and then come down here to specification of our cell size. So we need to specify the cell size in the X direction and in the Y direction, and I very, very strongly recommend that your cell size should be square all the time. You have to have a really good reason not to have a square cell size. So you can specify that as a decimal value, so I can put this in as 15 meters, for example. When I change the X value, the Y value is automatically changed, but then I can come and change the Y value if I want. So that's one way to specify the cell size. The other way to specify the cell size is as a fraction, and so a fraction is a numerator on a denominator. So this is our numerator for X, this is our denominator for X, this is our numerator for Y, this is our denominator for Y. If you're working with data that's in, well, it doesn't really matter if it's in geographic coordinates or in some projected coordinates, it can be a very good idea to use a fractional representation of the cell size. And that's because it eliminates round off in the raster system. So ProRaster will use fractional mathematics when it's working out conversions between coordinates and cell coordinates. And if cell sizes are specified as fractions, then it can eliminate round-off problems, which can become, significant for very, very large rasters. So if we're talking about, meters, then I might, if I wanted a 1 centimeter cell size, I'd put that as 1 on 100. So 1/100th of a meter, that's 1 centimeter. And once you've typed it in, it'll put it up here in your decimal, show you what you're looking at. When you're working with geographic coordinates, I always specify cell sizes as fractional. So if you want 1 arc second, for example, that's 1/3600th of a degree. And that's about 30 meters. So when I specified 10,800 before, I actually specified, that's a cell size of about 1 meter. So 3,600 by 3, that gets you down to 10 meters, and then by 10 gets you down to 1 meter. So that's about 1 meter expressed as a fraction of a degree. You can also put in the origin coordinate, and you don't ever have to do this. You do not have to set the origin coordinate. So if you don't understand what it is, don't touch it. The origin coordinate in ProRaster does not determine where the raster is, and it doesn't have any impact on where the raster is or can be. It's not the bottom left corner of the grid. It's not the top left corner of the grid. It is actually just the coordinate of the origin of the tiling system. So why is it there? Well, because it makes a difference to cell alignment. So if I put in an origin of 0, which is the default, then the edges of my cells are going to be some integer number of cells from 0. So the edge of the cell at 0 will touch 0. On the other hand, if I wanted the cells to be half a cell offset from that, I could put in an origin of half a cell. And in that case, that'd be 1 on 216,000. So I could put in 1 on 216,000. And that would give me half a cell offset. And there are some scenarios when you want to do that. And in this, so basically the origin gives you that capacity to shift where the cells align. It doesn't tell the system where the bottom left corner of the raster is. It doesn't restrict the raster in any way, shape or form. So, so that's the origin. Mostly you just won't touch it. So let's look at a few examples. So there's the one that we just ran. There's DC land use. Here's a geology map. So let me bring that in. I won't generate it in real time. Here's the geology map. That particular thing converted into a raster at some resolution. We can check what resolution that is. Let's have a look at the info. Whoop, come on up. 0.022278. I think that's 1 arc second. Hang on, calculator. Yeah, that's 1 arc second. So it's about a 30-meter resolution on that raster. And as you can see, as you drag your way across, it tells you what the geological unit is. Now remember, you can go to key plus all data table in the new version. And here's the classification table. So you can see that all of the columns from the original tab file have been preserved in there. And we can have a look at that. Let's have a look at a browser for that one. So here's all of our columns in map info, and various things in there, and all of that has been copied across into here. You can see the raster, the field, the band name, and here's the band value, and of course this label here is what's shown on the screen as you drag it around. So that's a geology map. The other thing that I wanted to talk about is raster size. So this is a very efficient operation. It can create very large rasters. This raster itself is quite large at 1 arc second resolution. The thing about classified rasters is as you go to very much higher resolution, smaller cell size, the raster itself doesn't get bigger on disk like you might expect. So for example, here we have a raster that's been generated at 30 meters, and we have 31.5 megabytes as the size of the raster. Then regenerated that at 3 meters, so it's 10 times smaller cell size, 100 times as many cells in that raster. But the size of the raster itself is only 10 times bigger on disk. So instead of being 100 times bigger, it's only 10 times bigger. And that's because classified rasters are very highly compressible. So you can tend to create them at very high resolution, and they're still a manageable file on disk. In fact, they'll be a comparable size file to the original polygonal data file. So let's go back into the processing dialog again. We'll do a bit of an example and we'll show you the rest of these things. So let me come up to Queensland Rural Property Boundaries. Let's have a look at it in Map Info, Rural Properties. Here we are. So here's Queensland, and this table contains a polygon for every rural property, every cattle station and so forth in Queensland. So you load it in. All right, so our name is going to be our label. We'll keep that one. We'll get our colour from the map info style, although in this case they're all the same colour. There's our output file name. What can I do? We'll make it 3 arc seconds, and we'll just spit it out. It will just take a moment to compute. And so there's our file. If we turn on some intensity, you can see the boundaries between the different polygons. Now we can do some different things with this. So let me close that. The first thing about this is that each property can be represented by multiple polygons. So you might say, okay, well I want to group those polygons together. So everything that's called Kurabulka, I want to group that together into one final class. So we can do that by using this grouping option. So I'm going to group on this name. So I've called this the label. And then I can choose to group by one of these special class types that I've already defined. And I'm going to group by that label. Output it to the same cells, same raster. Oops. Hit OK. And so now we're going to end up with less rows in our table because we're grouping things that are the same together. Now when I did my Kurabulka Landsat study, I didn't realise that actually there were multiple polygons per stations, per property. So I just used the main polygon for Kurabulka and completely didn't realise that some areas here down the south and up here on the north and on this edge were also Kurabulka, but they were different polygons. But now we've grouped them all together and we've just got one bigger polygon. Let me kill that off again. This is my label. Now I want to query. Or actually, let's just try a different one. Let's group based on local government area. So I need to select a one of these types for this. So we'll just call that the value, and then I'll group based on value. Let's go again. now you can see that we've got much larger polygonal areas. So we've grouped based on the local LGA, the local government area, and so now we have much fewer classes in our raster. What if we only wanted to get all the polygons from a particular local government area? Well, in that case, we can do a query. So let's go again. So I'm going to use that as my label, and now I'm going to query. So I'm going to query for all records in the table where the column local government matches the value, let's say Carpentaria. So when I selected this column, it went to the GIS table. It acquired all of the unique values in that column and then presented them in this drop-down list so that you can select one. So now we're selecting that local government area. Or maybe we can do it at high resolution because it's going to be smaller. And so now we just have the properties that were in that Carpentaria LGA. And here they are. One of the ways that I render these things often, in this case we have no colors for our polygons because no color came out of the GIS table. So what I often do is I use a lookup table color, I set it to no transform, and then I rotate the index through 16 different colors, and I choose pseudo color 16 as the color table. So now we're just rotating through 16 different colors based on the index, and that gives you at least a visual representation of the change from one classification to the next in your raster. Of course, you can also color by other columns in your class table. So in this one we have shape area, for example, and we can do a linear transform or whatever based on the area of the polygon. So this is our biggest, and these blue ones are our smallest. So that's the classify polygon operation, which converts a map info table containing polygonal data and as much metadata as you want directly into a classified raster that preserves all of that data, optionally groups it, optionally queries it, and can output it at very high resolution. Thanks for watching.